Hello, my name is Infantri Siahaan and I am a mechanical engineering student in Udayana University. And today I want to presenting topic about tool steels and high-speed steels. So the main reference that I took is from this book, Metallurgy for the Non-Metallurgy Second Edition by Arthur C. Riordan. Okay, we go to the introduction. Tool steels are a specialized type of steel alloy designed for creating tools, discs, and molds that shape, form, and cut other materials, including other steel alloys and non-ferrous metals, as well as some non-metals like machinable ceramics and polymers. The steels are also suitable for non-cutting applications requiring high temperature stability, wear resistance, strength, and toughness. They can be hardened through heat treatment with their chemical composition optimized to achieve desired properties for their specific applications. High-speed steels, a subset of tool steels, are named for their ability to machine and cut materials at high speeds. These are complex iron-based alloys that typically include elements like carbon, chromium, vanadium, molybdenum, or tungsten, and sometimes cobalt. The alloy composition is carefully balanced to ensure high hardening response, excellent wear resistance, resistance to softening at high temperatures, and sufficient toughness for industrial cutting use. The modern development of tool steels began with Benjamin Huntsman, clockmaker from Sheffield, England, who in 1742 developed the crucible melting process. This innovation enabled the production of cast steels, with carbon levels between those of cast iron and raw iron, allowing the steels to be hardened through heat treatment. By the early 18th, these steels were the best available for cutting and machining other metals. A significant advancement occurred with the Taylor-White steel, which could retain hardness at the high temperatures encountered during metal cutting, demonstrated at the Paris Exposition of 19. This tungsten carbide alloy allowed for higher cutting speeds, width, and depth, making previous tool steels obsolete. This breakthrough spurred metallurgical research that led to the development of many advanced steel grades used in tooling worldwide. Modern alloys. Following the success of Taylor and White, the early 20th century saw the development of many complex, highly alloyed tools and high-speed steels. These new steels included significant amounts of elements such as tungsten, molybdenum, vanadium, manganese, and chromium. They met the increasingly demanding surface requirements of industry and offered improved dimensional control and reduced cracking during heat treatment compared to earlier steel grades. First is tool steel properties. Modern tool steels are characterized by an exceptional combination of attainable hardness, rad hardness, toughness, and wear resistance. Attainable hardness is the capability to reach a specific level of hardness through heat treatment. Hardness, also referred to as hot hardness, is the capability to retain hardness at elevated temperatures. Toughness is the ability to resist breakage, chipping, and cracking under impact loading. Wear resistance is the ability to resist the effects of abrasion and erosion normally encountered by contact and interaction with outside source. 2. Grade classifications. There are classifications, presently more than 40 classifications of high-speed and tool steel alloys according to the American Iron and Steel Institute, or ICE. There are presently more than 40 classifications of high-speed and tool steel alloys according to the American Iron. For example, The IC classification system designed that ensures high-speed steels contain molybdenum as the primary alloying element. In the T-series grade, tungsten is used as the primary alloying element. 3. Rock tool steels. Rock hot work tool steels. Many manufacturing operations involve punching, shearing, or forming of metal at high temperature. Hot work steels, Group H, have been developed to withstand the combinations of heat, pressure, and abrasion associated with such operations. Rock cold work tool steels. Cold work tool steels, because they do not have the alloy content necessary to make them resistant to softening at elevated temperature, are restricted to applications that do not involve prolonged or repeated heating above 205 to 260 degrees Celsius. There are 3 categories of cold work steels: air hardening steels, also called Group A; high carbon, high chromium steels, also called Group D; and oil hardening steels, also called Group O. Other non-machining tool steel grades, in addition to the hot and cold work steels described, shock-resisting steels, low-alloy special-purpose steels, mold steels, and water hardening steels are also used for non-machining application. Next, effect of alloying and carbides on wear resistance. The wear resistance of high-speed and tool steels relies heavily on the characteristic of alloy carbides in their microstructure, including the mount, type, size, shape, and distribution. These carbides act like the cobblestones in a road, providing a hard surface that resists abrasion and wear. Various types of carbides can form based on the alloy's chemical composition, and they are typically identified by their chemical makeup. For instance, vanadium carbide in the microstructure has a 1:1 ratio of vanadium to carbon atoms, forming the Vc carbide base. Heat treating high-speed and tool steels. High-speed and tool steels intended for heat treating are normally prepared in a relatively soft condition with minimum hardness and maximum ductility, known as a spheroidized annealed condition. The annealing practice used to achieve this condition produces a relatively uniform distribution of the alloy carbides within the microstructure. Consider like this picture, which presents data showing the fraction of several alloying elements that have dissolved from the carbides into the austenite as the austenizing temperature is increased in an M4 high-speed steel. This steel contains 3 main carbides in the annealed condition: M23C6, M6C, and MC. The secondary hardening response that allows many high-speed steels to possess good red hardness is due to the precipitation of fine alloy carbides on tempering like this picture. However, this precipitation process requires that the alloying elements have been dissolved back into the austenite during the austenitization step. Polymer metallurgy tool steels. As a result of pronounced ingot segregation, conventional tool steels and high-speed steels can contain a somewhat coarse, non-uniform microstructure accompanied by relatively low transverse toughness properties. The carbide segregation observed in the longitudinal section of annealed M2 high-speed steel bars like picture illustrates the degree of segregation that is normally present in these bars and how it becomes more pronounced as the diameter of the bar increases. Most tool steels are raw products that are produced using traditional ingot casting techniques. An alternative process that is used to manufacture the same products is the rapid solidification of gas atomized powders that are consolidated to full density by hot isostatic pressing, or HIP. For example, the microstructure of a PM high-speed steel and a rogue high-speed steel are shown for comparison purposes. cutting tool coatings. In several cutting and machining applications used in industry, it is not uncommon to surface treat high-speed steels and tool steels with specialized coatings to reduce frictional contact, reduce thermal conductivity, and improve wear resistance. There are many surface treatments and treatment processes that are available. For example, it has been estimated that up to 60 to 70% of all carbide tools are now coated. The surface hardness produced by a number of different types of coating is shown in figure below. The material to be machined is an important consideration when selecting a coating. Yep, that's the end. Okay, that's all I can presenting to all of you. Thank you for your attention.